Great. Okay. So let's talk a bit about, actually, this may answer some of the questions that people had. So we started at this point. So we did this before. This is the models that are in there. We talked a bit about the single star models. I won't go too much detail about them. There's people here who know about single star models much more than me. I will talk a bit about the binary star physics that's in there because that's important. So our stars are all 1D stars, much like, well, actually, possibly 0D stars, and they're much like you get out of a single star detailed model. We only follow the mass and the core mass. Usually the core means the helium core, but if you're talking about a helium star that has a core, of course that core is made of carbon. It's not carbon and oxygen. It's not made of helium anymore. But we follow variables in the code like the mass, the luminosity, the radius, the things you'd observe. We also follow the core growth and also the core radius. We usually assume a solid body rotation for the stars. So we don't follow the internal structure and things like angular momentum transport in any of the detail you would in 1D detailed code. Usually this is not such a problem because many stars are very well mixed anyway, so that's fine. And also, I should also say, I think we don't really understand angular momentum transport in stars. People are still working on it. So it's not something we could easily put in. And even if you have detailed models, that doesn't mean they're right. So normally we don't have the internal structure. There were some exceptions to this. For example, in the paper I published last year on carbon and nitrogen in thick disk stars, these are stars that have mass transfer in the thick disk and look more massive than they actually should be. The thick disk stars should all be 1 solar mass or less. These are up to 2. Well, that's because they have mass transfer, fits quite naturally. So what I did there was to put in internal structure in tables. So I put in tables of the abundance profiles in these stars, and then I just transfer that abundance profile. So you can put in internal structure. It's put in afterwards as a sort of afterthought, perhaps. But as long as you've got all the physics you need in there, everything is fine. Most of the time, you only care about the mass and the luminosity and the radius of the star. You don't really care about what it looks like inside. So that's why it's much faster, because we neglect all of this. And we don't calculate things like diffusion in the star because of mixing and stuff like that. So that's all done in the stellar evolution codes that produce these fields. So we mentioned already that we've upgraded the lifetimes from 20 solar masses. We've also got the thermal pulses and the hot bottom burning. We've also got, compared to SSE, we've also updated a lot in the KICS code, and I'd like to thank the people who have contributed to that, some of whom are on the call today. A few things I put in recently. We updated the mass loss prescriptions. Hopefully Fabian can talk about that tomorrow because I think he's got a meeting today, but he'll be here tomorrow. He helped me with that. I've also put in things like hybrid carbon, oxygen, helium, white dwarfs. This is when you strip an early AGB star. You're left with a core that is made of carbon but has a helium layer that's thick on the top. And so you actually get different white dwarfs in those cases. And there's updates to the physics which are coming, and Gio will talk about that tomorrow. I don't want to go into that too much today. But the binary stuff that's important that you need to know about, I haven't really talked about binary physics at all yet, so I thought we'd better bring some in. In terms of orbital changes, there are many things you can do, and you have many options in the code. I'll talk about tides in a second, but just bear in mind tides are very important for post binaries. We now have 4 algorithms for magnetic braking compared to BSE's 1. And bear in mind that the algorithm in BSE I cannot derive, neither can Chris Tout. We have no idea where those numbers come from. And he said he had, apparently in his office somewhere, he has a derivation of this, but none of us could find it. So if anybody can derive Jared's formula, please tell me how it's done. I decided instead what I would do is go and get some more modern prescriptions. So we have things like Alison Sill's prescriptions in there, which I think you should use. That's probably preferable. But it's one of the big, if you're looking at close binaries, it's one of the big uncertainties. It's magnetic braking. So we need different prescriptions because I don't know which one is correct. And different people try to match what they find to observations, but it's always over a narrow mass range. And it's not clear what we should use. Gravitational wave radiation we have in. People love this these days because you're all looking at emerging things. We have the Peters formula, which I think is post-Newtonian approximation. You guys know about this better than I do. But I think it's good enough for what we do. I'll talk a little bit about this when we talk about time stepping as well. Now, other things that are important are things like angular momentum loss from winds. This is something for which there are several different prescriptions in the code. Angular momentum loss from winds is very easy to do when you have a fast wind or a massive star is fine. The problem happens when you have a slow wind in a binary that's like an AGB wind, and the binary is roughly the order of magnitude of the radius of the star. Then you have issues because you have tidal interactions and all kinds of complicated stuff. So we have several different algorithms for that, and there will be more coming in the next few years, I think, as well, because people are starting to model this with SPH codes and hydro codes in much more detail than they used to, including all the physics you need, like dust formation and acceleration and stuff like this. So it's actually quite a complicated problem. We also do mass transfer, of course. Now, this is both Roche-Lobe overflow and winds. So I'll talk about that in a minute. So in terms of tides, what do we have in there? Well, the physics is actually, it was all pretty much done by Pete Hutt in 1982. He wrote a wonderful paper on this. We have prescriptions for convective stars, radiative stars, and degenerate stars, mostly based on the timescales from Zahn. But I should say that if you look at the orbital evolution equations, the timescales themselves don't really matter too much. What's important is always the factor of r over a, that's the radius divided by the separation. It's to the power of 6 or 8, depending on whether you're looking at synchronization or circularization. I can't remember which is which, doesn't really matter. It's extremely nonlinear. So what happens is, as the radius of the star becomes roughly the radius of the orbit, of the separation of the stars from the orbit, then the tides become very efficient. We have some updates on BSE. One of the things that BSE does is the numerical stability is not great for tides. So what we have is an option called exponential tides. When the tidal timescale is very short, what we do is we fix the stellar evolution of everything else, and we actually solve the differential equation for the tides to give an effective derivative for the tides. It's a little complicated, but it's actually quite a standard way to fix very nonlinear problems like this. And the reason for this is that BSE, and indeed the standard way of running binary C, is it uses a forward Euler solver, which is not the most stable when you have very large derivatives. I'll talk about the solvers a little bit later, because that's something we've worked on a lot this year. Tom's also been working on tides in context of triples, so I thought I'd mention, he'll talk about that tomorrow as well. Now, mass transfer is a little complicated. We have, in very close stars, you have Roche-Lobe overflow, but then there's also winds and hybrids. So Roche-Lobe overflow, for those of you who don't know, and I'm sure that's none of you, is when the star gets so large, it overflows the L1 point between the two stars. So this is, the L1 point is essentially the point where there's no acceleration in the rotating frame, I should say. It's not just that the gravities are equal, but there's also a centrifugal term in there. If the masses are equal, then it is the gravities are equal. But we fit the Roche-Lobe radius according to Eggleton's 83 formula, which is still very, very good. I noticed recently there was a Mesa paper which tried to refit all of these things. I have no idea why, because honestly, it's much more complicated. Eggleton's formula is incredible. It's accurate to within 1% over the whole range of mass ratios, which is amazing. So we use that, and I think that's fine. Honestly, if you want to upgrade this, and you could get it to be more accurate. If you can make sure everything else is accurate to better than 1%, it's worth doing. But I don't think we're at that point. So it's really not worth it. So we have a mass transfer rate, which is a function of the radius. This is how we normally do it. So there's a fitting function which is used. This is based on what Jared Hurley and co did, but there's also an option in the code to use what Joke Klaas came up with in 2014, which is an updated form of this. The reason this is a problem is in massive stars, this fitting formula is not fast enough, which means the star tends to swell beyond its Roche-Lobe a lot. So if you use Joke's formula, it's much, much better. The radius is always slightly more than the Roche radius, maybe quite a bit more in some cases. But in the nuclear slow mass transfer case, the radius sits on the Roche radius and you get mass transfer on a nuclear timescale. When you have faster mass transfer, for example, when you start mass transfer from a more massive star to a lower mass star, it's always fast. You have what's called a fast case A type mass transfer usually. This is on a thermal timescale. That's what it's limited to. So this is also what you see in detailed models. So it's reasonably okay. It's numerically stable to do this kind of solver because you are setting the mass transfer rate as a function of your radius. That's actually the most stable way to do it. There's another way to do it, which is to use what we call adaptive Roche-Lobe overflow. It's adaptive in the sense that you change the mass transfer rate so that your star is always sitting just on its Roche-Lobe. I'm not sure whether physically this is absolutely correct, because stars probably do swell to be bigger than their Roche-Lobe at some point. But if you say R equals RL is your condition for mass transfer, that gives you a mass transfer rate. In the other algorithm, you're setting the mass transfer rate, so R is not quite like RL, but it's nearly. So it depends which of these two you want. Now, of course, if you're doing it adaptively, it's slower because you have to iterate the stellar structure solver to find a radius which actually sits just on RL. And that's quite hard to do. It gives you a bit more overhead. It also fails when this delta M, this mass you have to remove, is infinite. And that's the case of convective stars, for example. Because if you remove mass from a convective star, it gets bigger, which is the opposite of what we want to find a solution. So in that case, things get a bit uncertain, and it's not clear quite what should happen. Maybe you should then limit it to the thermal rate. I don't know. So this worked in the paper we did with Fabian on main sequence mass transfer. And I think for main sequence stars, that's fine, because you expect them to shrink when you remove mass. When we were on the giant branch, we then switched to the other formula for this. So it's kind of a hybrid scheme in that regard.
Do they give a very large difference between the two if you use?
That's a good question. I can't remember. This was 5 years ago. I'm not sure I remember. Not usually. I think you still see the fast case A, and you still see the slow. So you get a fast mass transfer until you invert the mass ratio, and then it slows down, which is exactly what you expect from detailed models. If you use the class formula from 2014, it works very well. They look quite similar. If you use the Hurley formula, they don't work so well because that underestimates the mass transfer rate, and the star gets made way too big. The class formula is currently the default in the code because I believe that. So there can be differences, particularly in massive stars. It's less of an issue in low mass stars, but in massive stars, it is quite a big difference. We also have tests in the code for dynamical mass transfer. That is when the mass transfer becomes unstable. For example, if you have a common envelope, it forms often because the red giant is transferring the material. You remove material from a red giant, it gets bigger, which increases the mass transfer rate, which means you have more mass transfer and it goes in a positive feedback loop. We do this based on critical mass ratios. There are different critical mass ratios for different stellar types. In the modern binary C, you can specify these for every single stellar type. So if you give it a positive number, it assumes that's a critical mass ratio. There are also algorithms we have for this. So you can choose the critical mass ratio to say be a function of mass, core mass, metallicity, whatever you want. We have several different algorithms also which you can use. And people have studied these quite a lot in the literature. A group I was visiting last week in China have done a lot of work on this. So that's quite useful. And compared to the original BSE, which has only one set of numbers. And it's much harder in BSE to actually change what those numbers are. In our case, they are just parameters that you set. In BSE, you have to go and hack the code and find it yourself. Good luck. I'm not going to do that for you. So, other things like the Darwin instability is naturally in the model because that's actually just conservation of angular momentum. So angular momentum is conserved. That leads to stellar mergers, for example, which we then treat very similarly to BSE. So they're actually not so difficult to do. Common envelope evolution is a pain and one of the big uncertainties in stellar physics at the moment, and still will be, I think, for the next whole career, I think, for most of us. So we have a stellar evolution, well, let's say everything is based on the BSE prescription for common envelope evolution. It's been expanded a lot to include accretion onto the other star that's spiraling in. We have ejection, we have mergers sometimes, we have an example of some of the physics in this. The way this is done is you have this alpha parameter in common envelope evolution. This relates how much of the orbital energy you can put into the envelope to try to unbind it, essentially. So your envelopes, your distribution of separations starts as this pink curve here. This is the separation just before the mass transfer. And these other two curves here are the separation just after with different alphas. So depending on what alpha is your star, you can change how much you spiral in the star. There's also this parameter here, which is lambda. This is the binding energy of the envelope, or 1 over it, essentially. we have two choices. You can either use a constant for that, which is what people did in the old days, and indeed some people still do, or there are fitting functions to the Dewey and Towers papers from the late 90s, early 2000s, which give you an idea of this. Beware, using those fitting formulae for non-solar metallicity will give you problems because they are only for solar metallicity stuff, especially on the AGB. But at least you can use a prescription for this. There's another couple of prescriptions in the code now as well. And these lambdas are one of the things we're going to get from the updated stellar physics later this year, early next year. Hopefully. Looking at next year. So we usually use the alpha prescription. We also have the gamma prescription, which is the Neylemans and Taub paper, where instead of looking at the energy, doing the energy balance, you look at the angular momentum balance. So you remove angular momentum from the orbit, and this gives you a very different prescription. I'm not sure either is correct, but that's how it is. So alpha and gamma are kind of free parameters. Oh, sorry, alpha and gamma, it's free parameters. Alpha, of course, should probably be less than 1, as should gamma, because you don't want to invent energy or angular momentum. But I should say the alpha that's in here is only the orbital energy. There are other sources of energy you might consider, like, for example, if there's nuclear burning, that could contribute some of the energy that ejects the envelope. That could be. It's a bit much to put alpha greater than 1. It's just a numerical test, really, because if you want to put alpha greater than 1, you are saying that your extra source of energy is proportional to your orbital energy, which is probably not true. You can do that. We have some new physics in there, which is not in BSE. So there's some Nandes and Ivanova paper. Ivanova has a whole group in Canada who are working on common envelope evolution. So I keep trying to put their results into ours. They have suggestions for what alpha should be, for example. So we have Dewey's models for the fitting formula. There's also the Wang paper, which allows you to fit lambda as a function of mass and stuff like that as well. Beware that often these fits are over very narrow parts of the parameter space, so you've got to be careful. This is one reason we're trying to make model sets ourselves, is because then we can make sure we have these numbers over the whole parameter space. The other new thing that isn't in any of the other codes are post-common envelope circumbinary disks, which I'm working on with Gino, who's coming at the back. So I've been working on that. That's all very new and very, still buggy, of course, as new things tend to be. But it works reasonably well. But I can talk about that later if anyone's interested. In terms of winds and mass transfer from winds, we use the Bondi-Hoyle-Littleton standard accretion rate with a multiplier. Of course, this is only really valid for fast winds. If you want to use low velocity winds, you can also look at the wind Roche-Lobe overflow prescription we have in there. There's a series of papers by Carlo Abate on this. I'd suggest you go read those. They're all implemented, and they all use binary seed testers. These are based on Shazri Mohammed's works. There's a couple of prescriptions from him. What's going on there is that the wind is so slow that as it comes off the red giant, it actually gets funneled towards the secondary. Kind of like Roche-Lobe overflow, but it's not quite. It all depends on where the wind forms dust, because that's where it accelerates and becomes fast. It's quite complicated physics, and there's still a lot of people working on this. I think Onno had a student working on this until recently, so there's a lot more papers out there and things that could be implemented. But we have rotationally enhanced winds, so when you accrete material onto the star and you spin it up, we have a few prescriptions for that. We've got Norbert Langer's prescription, we've got the Mene and Medea prescription for that as well. I don't know which one you should believe. You can try whichever you like. It's fine. They disagree with each other, so that's how it is. They often do. That's fine. We also have the companion reinforced attrition process, which has the best acronym ever. They've recently renamed it to the tidally reinforced attrition process, but I like companion. That's how it always was. Peter Eggleton said it took him 2 weeks to go from crap to this, so it's a good acronym. What this does is that when you spin up a companion red giant in a binary, you increase the mass loss rate because of the spin up. And this was done back in the late 80s by Chris Taub. They fitted it to Myra's, I think, so it is fitted to observations. This is something I think we really need to look at again, because this could actually be very important for keeping the rotation rates of these stars lower than they otherwise would be. Something that turns out to be quite important.
Sorry, but this enhances the mass transfer.
The mass loss rate from the red giant.
How is this different than the rotationally enhanced winds?
because it's supposedly tidal rather than by mass transfer. I don't know exactly. It's a different prescription. That's all. Yeah, that's all. So the mass loss rate in their case depends on the binary separation, for example, which is not the case in the rotation enhancements. That just depends on the spin of the star. So it's a different prescription. I don't know which is right, but you probably shouldn't use the two together because they're probably saying something about the same thing. So, yeah. Now, in response to mass transfer, of course, you can change the stellar type of the star. So if you accrete hydrogen onto a helium star, you make it back into a hydrogen-rich star. That's fine. We also have rejuvenation. This is like blue straggler formation in globular clusters. We see that quite commonly there, but also in other systems. We updated that based on the stuff Selma did in the code back in 2014, I think it was, that we published that. Also, if you have mass transfer, you can have explosions. So we'll talk about novae tomorrow. Hopefully, a few people talk about them. 1A supernovae are related to that, possibly. Nobody knows what 1A supernovae are, so it's fine. One other thing that you do is when you spin up a star, when you accrete. Now, how you treat that is actually quite important for a lot of stuff. So we have a scheme here which means that if you try to accrete too much angular momentum, you put it in an excretion disk. That's one thing that we have, for example, instead of putting it in a wind that's enhanced. And I think that's actually more physical because this material should never accrete in the first place. So presumably it then sits in a disk and is ejected at some point. But again, this is stuff that is, it's there for you to try, and you can have a look and see what effect the physics does. I'm not trying to sell it as something that is right, but it's something you can at least try to match what you see. Now, nuclear synthesis. This is the thing that we really do that nobody else does, or at least I've been doing for years, nobody else does, in a rapid population code. I mentioned the thermally pulsing phase. This is something we have based on Amanda's models from a little way back, but I think they're probably okay. We have first, second, and third dredge up all in there, so you can follow the abundances at the surface of the star and see how they change when you have all these different dredge ups. We also have hot bottom burning, so I actually have proper nuclear burning code as part of binary C. It's a very limited network, so it only does CNO, neon, sodium, magnesium, aluminium, but that's all you need for hot bottom burning, at least in these models. And you can see from the diagram here, this is from my 2006 paper where we looked at the uncertainties in nuclear reaction rates and what they do to the chemical yields compared to the standard. And we can do that very fast in this code. And each of these models would take a second to run. And then we can do it then over a large parameter space, including the uncertainties in 10 different reaction rates, which you could never do with the detailed stellar code. So that was kind of fun. And indeed, had a lot of discussions then with people working in nuclear physics about what, for example, the error bars in nuclear reaction rates even meant. At that point, I couldn't get a straight answer from them. Now there's a whole section of nuclear physics which looks at this. And this was the paper that set that off. So it was really, all these Monte Carlo models they're doing are based on things like this. I mean, the way it's done now is a lot better than we did it, but that's okay, that's progress, that's fine. We also have a table of S-process abundances that are dredged up in AGB stars. Again, all you need to know really is the thermal pulse number and the core mass, and you can get yourself how much S-process. There's also a tunable parameter for how much S-process you might want. There's a couple of grids in there for that. The Galeno-Busso-Lugaro one is probably the standard. There's also one that Amanda made, which Carlo Abate was trying to put in the code before he left Astro. I have no idea how much of that is still in the code, but yeah, the standard one is very complete. But again, this is physics that could be updated with newer codes. Maybe maybe Alex can persuade Amanda to sort this out. That would be quite good. Supernovae. When you have a supernova, we have code that can kick both the exploding star and the companion star. So if you hit the companion star with a shockwave, you can kick it as well. And we can do accretion onto that as well. So that's all included. You can change the kick velocity and the dispersion, say the sigma in the kick velocity functions, normally a Maxwellian with a certain dispersion. You can change that for each different type of supernova. So that's 1B, 1C, type 2, gamma ray burst, whatever. They each have now an individual tunable kick, which again is an improvement on BSE, which just has 1 or 2 functions. That's it. At the moment, the way it's done is standard is to do a Monte Carlo. So that means that when you have a supernova, you randomly choose your kick direction. So it could be anywhere in 4 pi. And you then sample from the Maxwellian to give it the velocity. You can get it to repeat that process. So there's a parameter in the code which allows you to repeat at that point. So you can stop the evolution and start it again there. And you can then sample the parameter space for where you want the kicks to go. For some of you, that may be very useful. As for yields, we have different core collapse methods. So you can either use the Worsley-Weaver yields. These are very popular in the literature still, I think people use these. But we also have, in order to get those right, you need to use Portinari's method, I think from the 98 paper, because you have to remove the envelope to match them to your stellar models, because you have different wind loss to what they have, which was known, I think, in the models. You could use the Kiefian-Limongi yields, which are far superior, and the reason they're superior is you can not only have a much bigger grid of models, you can choose your mass cut in those. So, for example, that is how big you want your core to be. The big uncertainty here is the neutron star mass. Right? So how do you set the neutron star mass, which is your mass cut in this case? We have several different prescriptions for this in the code now. These give you very different neutron star or black hole masses as a function of your pre-explosion core mass. I'm not an expert on this. There are people in this room like David who knows much better than I do, like know much more about than I do. There's people who are on the chat who know much more than I do as well. But we have prescriptions for that. There's also a couple of prescriptions for doing our process, if you want to do that from supernovae. And there's also a set of yields for electron capture if you want to have ejection from electron capture. At the moment, the standard is that there's no material ejected in an electron capture supernova, because I have no idea whether there should be. It's not clear. No, does anybody know? I have no idea. Just a collapsing core. Why should it? It might be very small. We also do type 1As, so there are various different type 1A prescriptions, the reason being that nobody has a clue what type 1As actually are, and that's why people get working on it. That's good, except that they're probably exploding white dwarfs. That's fine. The sub-Chandrasekhar edgelit detonation yields we have from Livni on our net from 95. It's pretty old, but no one's really worked on them since, so it's fine. There's a lot of updates to the Chandrasekhar mass exploders. So the original one we put in was the D2 model from Iwamoto. The reason for that is because they provided very nice yield tables, whereas the old W7 didn't. It's like W7, for those of you who know about these models, very similar to that. We also have Ivo Seitenzaal's new grid from 2013. This is a whole set of new yields with different numbers of ignition points inside the star, so there's a lot more parameters to it. You can try them. They work quite well, they're fine, but I'm not sure which one's correct, but you can try them. We also have helium star explosions. This is when you merge two helium stars, because it was originally thought those probably explode. I'm not convinced they actually explode, because you see lots of explosions we don't actually see, but you can turn it on and off if you want. Accretion-induced collapse we have there, but at the moment we don't have a yield for that. You can detect it in the code. If anyone knows how much yield should come from an accretion-induced collapse, please tell me, and I'll put it in. It's very easy to do. But at the moment, there's no yield, so we don't actually need to put anything in. And also X-ray bursts. We could put those in quite easily. These are where you have material accreting onto a neutron star. Now, we know X-ray bursts happen. We see them. As far as I know, the current yield from an X-ray burst is not thought to be significant, in that the material, when it ignites on the surface, doesn't actually get ejected, which is not surprising because the neutron star has a lot of mass and gravity is very strong. If we do eject material from X-ray bursts, the nucleosynthesis signature should be very interesting, but we'll see. I'm not sure about that. We have a lot of stuff on novae, and this is something I've been working on with a lot of people who are here today. The yields for novae, this is the chemical yields, so the amount of lithium, carbon, things like that. They come from Jordi Jose's grid from 1998. It's still pretty old. But every time I ask him to update it, he says, well, it'll look the same. So that's fine. I keep pressing it. Maybe you can send in messages and get new yields. But now, how we treat what happens to the mass in the novae is tricky. There are a lot of different prescriptions in the literature for this. The original BSE code just took a fraction of the accreted mass and blew it off. So let's say you accrete some amount of mass, you blow everything off except a small amount, well, that's your nova yield amount. Yoga class put in prescriptions based on Nemoto's works for this, which are a bit more quantitative. Those are also an option in the code, so you can choose which ones you want. Now, something I've been working on quite a lot in the last year or two is how we actually evolve Nova systems. And we have 3 ways of doing that at the moment. BSE has a prescription which is a very time averaged, so you can have very long time steps. And what you do then is you have an accretion rate, and some fraction of that accretion rate is ejected as novae. This doesn't really simulate individual novae. This is just an average over, over many years. We can also implement individual novae in the code now. So each individual nova is followed. So you have very short time steps between the novae. And that's great if you want to look at the yields as a function of nova number, which is what Arman hopefully will be working on. But of course, it is a huge computational cost, particularly when you have, say, a 1.38 solar mass star, and the time between the novae is very short, it can be like years. And so then you end up with time steps, which are always very short for many gigayears. So you end up with a huge computational problem. So I've also got a hybrid scheme in there, which allows you to do the first few hundred novae. You can tune the number to whatever you want. You can do the first few hundred novae with individual novae, and then you use an average scheme afterwards. So you bunch them into groups of 10 or something like that. And this, I think, will be okay because we expect the behavior to be asymptotic. So once you get to a stable state, it will asymptotically be similar, and then we can do that quite the same. There are also other things from Mike Shower's papers in the 80s. You can do accretion onto the donor star, so when you have the explosion, it hits the donor and you accrete. That's also in there. And there's also his angular momentum loss system, which you can read his papers if you care about that too much. It's implemented, it's not switched on by default, but you can turn it on if you want. Now, in terms of chemistry, the mass transfer, of course, is important because when material hits the secondary star, it's accreted onto it. But what happens to the chemistry of this? Now, we assume that thermohalide mixing is very quick. For those who don't know, thermohalide mixing is a thermal timescale instability when you have material on top, which has a higher molecular weight than material underneath. In normal stars, this never happens except in very rare cases. In binaries, it happens a lot. So the material that accretes will be carbon-rich, barium-rich, probably helium-rich if it's had some stellar evolution. So it will have a higher molecular weight. It then, we assume in our model, it instantly merges with all the rest of the envelope. We did a series of papers on this with Richard Stancliffe back in the 2000s, and we looked at this, and it's actually a very good approximation to what happens in most cases. So for example, for carbon stars, barium stars, things like this, you would expect this dilution to be very efficient. Now, in the nucleosynthesis algorithms, the metallicity does not have to be in the BSE range. It could be 0, or it could be several times solar. So we have 3 metallicities in the code. There's a variable called metallicity, which is the one used for the stellar structure. So that's all the fitting formulae. The nuxin metallicity is used for nucleosynthesis. Usually they're the same, but you could set it to something smaller. What you will then do is use the lowest possible metallicity from the stellar evolution, and nucleosynthesis should just work for others. There's also a new one, which is called the effective metallicity. This is used in wind calculations. So for example, Fabian Schneider wanted to look at what happens when you have very, very metal-rich stars and what happens to the winds in those. Now, we couldn't do that with BSE because it only goes up to a metallicity of 0.03. But you can set the effective metallicity to say 0.1 or something if you really want. And the wind prescription will be extrapolated to 0.1. I mentioned a little bit the stuff we did last year on the carbon and nitrogen in thick disk stars. This enables you to do algol-like mass transfer. So if anyone knows about algols, this is where if you look at algols, they transfer material to the companion. The algol we see now is nitrogen-rich and carbon-poor because you've stripped down into layers inside the main sequence star, which are nuclear brittle. So we can do all of that now, carbon and nitrogen. And I'm trying to persuade Geo that we should do it also for neon, sodium, and things like that. He's a bit skeptical about that. Now, one thing that we have that I should mention that could be improved are the surface abundances in massive stars. Because massive stars have mass loss that's quite important, especially on the main sequence. Now, the way we do this is we fit, and we have tables to rather, a set of models that Richard Stancliffe gave us. There's fitting functions to Lynette Drey's models, which are 20 years ago as well. And you can then fit the abundance as a function of the strip mass in the star. I think we can do that better, I should say. I don't think what we have now is ideal. It was a fast way of doing it, and in those days the computers weren't so good. So maybe that's something that we need someone to work on in the future. So if you care about surface abundances in massive stars that are stripped, that's something we could improve. It's okay, but it's not great. In terms of initial abundances of the stars, there are 9 different options for an initial abundance mix at present. You can choose which is your favorite. The Anders and Graves paper from 1989 is very common in stellar evolution, but we have also many other things that you may want to use, sort of Asplin's mix and stuff like that are more modern. We also have a set of algorithms for experimenting with lithium. This is whether you want to increase lithium abundances on the giant branch, things like that. So I put that in for George Angelou, who's, I don't know whether George is still working in Astro at the moment.
He applied to postdoc with Ilya Mandel.
Oh, really?
That's his last call, basically. If he doesn't get that,
We should. Anyone that knows Ilya, some people here do,
Yeah.
please find some blackmail material on him so we can force George to get a job with him, because George is great. So. Andrea. So essentially, that's all the nuclear synthesis and physics that's in the code. And I think for those of you who've never used it, that gives you an idea of all the stuff that's there. It's quite a lot of stuff. All right. You don't have to change most of it. The defaults are there, chosen to be reasonable, justifiable. They may not be quite what you want. They may not also be physically correct. In many cases, we don't know exactly. But I think that's no different to using a detailed stellar code. If you download Mesa, there are a lot of options, many of which you don't know what they do. And that's actually one of the problems in Mesa, is that people run it with all these options and not really understand it. But here you have documentation for all of these, so you can always ask them as well if you want to know what they are. So what's the time? It must be lunchtime now. Oh, really? So do we have any questions? Is the audience still there? Have you all gone to sleep?
Still there.
Hey, good. So are there any more questions from anyone? I presume you'll think of them over lunch or something, and then we'll come back.
I have a few on some points that you were mentioning here and there. There may be updates, so correct me if I'm wrong on some of them. So I think one important mention would be that in the mass accretion rate from the secondary, there has been a calibration from Fabian Schneider in Schneider 2015, I think, which is that the accretor accretes on its own thermal rate, like in its Kelvin-Helmholtz timescale.
Yeah.
But there was a calibration of like a factor of 10 in front of it when the adaptive Roslov overflow that you explained has been used. I don't know if this is still like the up to date what we have, what is the default in binary, or if anyone has checked any more on that one.
So
I'm just mentioning that this 10 is coming from that paper, from that calibration, which is important because it has been calibrated in binary C.
So when you accrete material on the secondary, you can limit that according to some multiplier times the secondary's thermal rate. And that's a free parameter. You can calibrate that however you like. That was originally introduced, I think, in the BSE paper in 2002, originally. So that's where you want to find the original reference for that. Fabian was using a similar thing based on what they were saying. The reason for this, of course, is that you don't want the secondary to accrete too fast. And if it accretes way beyond its thermal rate, of course, then it will just swell up. And so it's assumed that if that happens, then the material is lost from the system. It's not a perfect solution. But again, there's no really easy way to do it otherwise.
So what is this factor by default in binary C right now? Or is it is it changeable, or is it on?
It's whatever you like, yeah, sure.
Okay.
I'll go through how to change all these factors later. Accretion limit thermal multiplier, there we go. So it can be whatever you like. It's
okay. I'm just saying for people that may want to use is that there has been a mass accretion calibration on that paper on 2000.
I'm not sure how it was calibrated though. I don't remember, so it'd be good to check that.
It was, I think it was in a way to reproduce that your bet, like your fraction of accreted material is around 1 for early case B and around 0 for late case B.
That could be. That sounds about right.
That was the calibration. And just another comment for everyone who's been using this. I remember that when you accrete mass hydrogen-rich material onto a helium star, this has to become again a giant. There was again, maybe this is old, but I remember that it was not by default this at that point. So maybe now it is, and people, just people to be careful not to make a bigger helium core.
No. So at the moment it would form a core helium burning star.
Okay, nice.
Which I think is what it should do.
And
then you have an issue because you have a core helium burning star with a very thin envelope.
Yeah.
And sometimes the shell burning speed is faster than your mass accretion speed, which means it should be a helium star. So it's quite a difficult problem. It's not an easy solution.
Yeah.
Or rather, the growth of the core will be faster than your accretion rate. So in that case, it probably should remain something like a sort of hybrid helium star.
Right. Just wanted to mention that people. I remember that there was like a flag that you needed to open to turn on for that one. And
I think that's all included now by default in the new mass transfer stuff. That's come in the last year or two. We've completely rewritten all of the mass transfer stuff.
Okay, that's good. And my final is a question. So you mentioned for common envelope, you mentioned something from Nandez and Ivanova, but so what is exactly this? I didn't get exactly what are the details of that one. And are these implemented, or you're asking them in order to get something implemented?
No, it's based on their 2016 paper. They have a slightly different prescription for how to treat the I guess something like the alpha parameter.
And this is in binary C right now?
Yes.
Okay, as an option. Okay.
Yeah.
Good to know.
So you can try that if you want, but I would suggest you read their paper to find out over which part of the parameter space you can do it, because it's not for the whole parameter space. It's based on detailed hydro models, which are, as you can imagine, expensive. So they haven't done every massive stuff. So
yeah. Okay.
And I'm quite happy to put other people's in as well. There are other prescriptions out there. Every time I look at them and it's just for a 1 solar mass star, I think, well, that's not much use for a stellar population, but that's how it is. It's difficult to make hydro models for every single mass. That's the thing.
Does binary C give warnings when you're using options outside of their defined parameter space?
Sometimes. For example, if you try to merge two masses and make them bigger than 100 solar masses, I think it is at the moment, it will trim your star for you by default, because it would rather run a star that it actually believes than one that it just doesn't know how to work. But really, it's up to the user to work out where these things are valid and where they're not. Most of the time, the documentation, certainly most of the time, will tell you it's not in certain regions. Just stop it. I don't know what to do when it's out of the range. You see, do you want to stop or do you want to extrapolate? It's difficult to say. That's always a problem. But I think most of the stellar physics will be okay as by default. Because if you try to evolve a 200 solar mass star, it will turn it into a 100 solar mass star with a warning. But you can disable that feature. That's fine. That would be dangerous. But for things like the alpha prescription in common envelopes, we assume it's valid for all masses, all separations, because we know nothing better. So in that case, it's very hard to say when it's not valid, because we don't know. That's the problem. And I think that's true of most of the prescriptions that are in there. If they have, say, a validity range, if you talk about the mass loss rates, for example, then the massive star mass loss rates, of course, will only apply for massive stuff, so you're fine. But if you're looking at, say, the rotational mass loss, extra mass loss because of rotation, if you turn that on, it will apply equally to low mass stars as high mass stars. But to the best of my knowledge, no one's ever tested it for low mass stars, only for B-type stars and things like that. So I don't know whether it's applicable there. But that's a good question. Maybe that's something we need to look into. Any other questions from anyone?
Can you guys hear me?
Yeah.
It's quite a specific question, but for the ELD stuff, where you're using the yields from Livni and Arnott,
Yeah.
I was wondering if I was to contrive an ELD scenario where instead of destroying a CO white dwarf, I instead did an oxygen neon, those yields would be useless, right?
What do you mean by useless?
As in, like, would it be, would they be at all relevant?
That's a question. I think it's really a question for Dave Arnett.
Yeah, I mean,
I
know they
right.
did them.
I think you're right.
On
They
CO
wouldn't-
white dwarf.
I think they would not be appropriate. That's true, because they're for carbon-rich white dwarfs, and you no longer have any carbon, and so your explosive yields will be quite different.
Can you think of any, like, as far as I can tell, no one's ever actually done a proper model of that scenario. So in that absence, can you think of like a
That's
best
probably
guess?
why there aren't any models in binary C as well. I mean,
Yeah, probably.
So if you want to do that, you would have to then go away and run detailed models of those explosions. There's no easy way to convert from a carbon explosion to an oxygen-rich explosion. I suppose you could say, oh, my carbon is oxygen. That would give you a very rough idea. But then, of course, the energetics would be completely different, and you'd end up with, I mean, Morgan's looking at me very dubiously here. He probably knows more about this than me. I think it would be very dangerous to do that.
Yeah.
So if you wanted to do it, you'd have to go away and run some detailed models of explosions of those stars, and that's not easy.
Okay.
I'm sure Mesa can do it. Doesn't mean it's right.
Sure.
Well, Mesa can do everything, right?
So other than the fact that the yields from these, I don't know, ELDs and oxygen neon white dwarfs would obviously be incorrect. If I had, I mean, at the moment, just to make this code stop complaining, I just said, all right, use the yields anyway, even knowing they're wrong. Yeah. That wouldn't have any obvious knock-on effects to other stars, right? I could still trust the yields for other things.
No, I think everything else would be fine. That's okay.
Right. Cool. Just check.
Yes.
Awesome.
I mean, for the ELDs, are, of course, they're not in favor at the moment as a way of blowing up white dwarfs. For those who don't know what they are, it's where you accrete hydrogen onto a CO white dwarf, forming a helium layer on the top, and then the helium layer ignites at the edge, which causes the whole star to go bang. Now, this was quite popular back in the 90s, I think. I'm not sure if it's currently considered a way that 1As explode, but who knows? Yeah.
Just this year, actually, very recently, there was a paper by, I think it was, might have been Bildsing, I think, who claimed that in 2D, they got a ELD scenario to produce a type 1A looking explosion. So good nickel and light curves. So I don't know.
Maybe they
some
do
people consider it, at least.
Then the question is, how much mass do you need to accrete? And so that's a number that I think was 0.15 solar masses in BSE. I'm not sure whether that's right. It probably depends on the mass of the white dwarf as well. So, but you can put in a prescription for that. That's easy enough to put in. So.
Yeah, definitely not very well understood. So, yeah.
Keeps us in jobs. Don't worry. Good.